Are you one of those people who sat in maths class and wondered, when will this stuff ever be useful? Well, your long wait is finally over. We're at the 17th meeting of the Maths in Industry Study Group right here at the University of Zululand in South Africa to discover how real-world problems are being solved with mathematics.
Well, we drove here this morning through fields of sugarcane, which is appropriate because we're at the University of Zululand for the Mathematics in Industry Study Group, and we're asking how mathematicians and mathematics can improve sugar production. What have maths and sugar got in common? Well, you're about to find out how photographs and artificial intelligence can be used to save water and energy in sugar production. Doesn't that sound sweet? To kick off this conversation, I'd like to introduce you to a number of guests who are collaborating at the Mathematics and Industry Study Group. And first is Dr. Richard Loubser, who is a mechanical engineer at the Sugar Milling Research Institute. And he is the industry representative who has presented a problem at this year's event. Richard, can you tell us a little bit more about the sugar industry in South Africa?
The South African sugar industry is centered in Natal and in Mpumalanga, and there are probably more than 1 million people who depend on the sugar industry, both directly and indirectly for their livelihoods. The sugar industry is currently experiencing difficulties in growth. The sentiment towards the use of sugar has had a huge impact on the sales of sugar, and particularly competition from overseas. The Brazilian sugar industry far exceeds their domestic consumption, so there's lots of sugar on the international market, so we have to look at other products in order to survive.
And how long has the sugar industry been operational in South Africa?
The sugar industry started in the mid-1800s and has continued since then, grown a bit, and currently we're seeing quite a shrinkage in the industry itself.
And perhaps you can start by telling us a little bit about how you get sugar from sugarcane.
The process I'm about to describe actually was developed in South Africa. Unlike other countries where they use mills, in South Africa we use a device called a diffuser. What happens, the sugarcane is delivered to the factory. The cane is then shredded and fed via conveyor belt into a large machine, which is essentially a washing machine, where water is added, and that water washes the sugar out of the sugar cane and is collected as juice, which is then concentrated in evaporators. The evaporated juice, now syrup, is then fed into a device called a pan, where further evaporation is done, and then seed crystals are added, and the sugar in the syrup deposits on the sugar crystals, and they grow up to the size of sugar crystal that we use. After this, the mixture of residual syrup or molasses is separated from the sugar crystal in a centrifuge, and the sugar crystal, which has a brownish layer over it, known as raw sugar, is then dried and either bagged or sent for further processing in the refinery to make white sugar. The extraction process separates the juice from the plant fiber. The plant fiber has several uses. The main one in the factory is to burn it to make steam. Steam being used for running turbines, and also, once it's been used in the turbine, it is used to evaporate the water from the juice.
And that's really where the problem that you've brought to the study group arises, isn't it? Can you explain why it's important to use just the right amount of water to extract sugar from sugarcane?
The water that we introduce to the sugarcane to wash out the sugar has to be evaporated. Now, to evaporate the sugar, we need to use fuel. If we put too much water on that sugarcane, we need to burn lots of fuel in order to evaporate that water. If we have spare bagasse, that fiber from the sugar plant, we can then use that for other purposes. And because we can use it for other purposes, we can make more money and reverse the downward trend in the industry. If you put too little water on the cane to extract, of course you won't extract all of it, and you will be wasting the sugar which you could have extracted. You'll be burning it in your boilers.
Right. So many of these industrial processes are about looking at any opportunity to reduce wastage. And so what I'm certainly hearing is that by adding too much water, you'll end up using energy to drive that water off again in the crystallization process. And by adding too little water, you'll end up pushing sugar or allowing sugar to end up leaving with the waste plant material. Is that right?
That's correct, yes.
So how are these decisions currently made? How does the process, or how is information fed into the process about how much water is the right amount of water, given that presumably the sugar cane that's arriving will have different properties from time to time?
At the moment, that is not very closely controlled. What we do is we measure the amount of plant fiber entering the extraction plant, and then there is an allowance of the amount of water added based on that fiber entering the extraction plant. So it's really a delayed process. We aren't able to closely control that process at the moment.
Okay, and that brings us to the point at which you've brought an idea to the industry, mathematics and industry study group, to say, is there a way in which we could improve that process? What's the idea that you've got in mind?
We need measurements in order to make these decisions, and the measurement is properties of the cane, percolation properties of the cane. And the thought we had at a brainstorm was, can we use pictures of the cane in order to get those properties? This is based on the idea that an engineer would walk up to the conveyor, scoop off a bit of cane and actually look at it and say, oh, that cane's shredded well, or that cane's not shredded well. And we started asking the question, can a computer start making these decisions for us so that we can get real-time feedback to make adjustments in the plant?
So if we're talking about computers making decisions, we need to start talking to some other people. And we've got Thabang Matonzi here. Thabang is the Chief Technical Officer of an artificial intelligence firm, Afrilytics, and he's also a PhD candidate and a lecturer at Wits University. So Thabang, what is the way in which a machine could be used to make decisions of this nature?
Oh, thank you for having me on the show. So the techniques that we'll be applying directly are from a discipline in computer science known as computer vision. So computer vision is the act of trying to simulate the way that a person or an individual actually sees, and try and simulate that using computers.
So once the computer has, so this is the idea of taking a photograph of the shredded sugarcane and showing that to a computer. How does a computer make sense of that photograph?
Currently, one of the algorithms or architectures that we're using is a convolutional neural network, which is a well-established, well-documented network. How it works in basic terms is it takes the image and puts it through a set of transformations. So you can imagine taking up a photograph of an individual, but some way, somehow it's obscured. If you put on your glasses, you're able to recognize them better. If under different sets of lighting, you might have a better idea who that person is. So the CNN, or convolutional neural network, works in exactly the same way. It takes the image and transforms it until it learns particular features of that particular image.
Okay, a convoluted neural network sounds a little convoluted. So can you tell us a little bit more about what is a neural network? These are one of the building blocks of artificial intelligence, am I correct?
Correct. So there's two main subfields or manners in which we can phrase a particular problem. So we come across unsupervised learning, which is not relevant for the purposes of this talk. What we're dealing with here is supervised learning. So you have a set of input data, and which is characterized by certain features, and you have known structured output allocated to that.
When you talk about input data, can you make that real in terms of the current example?
Sure. So what we have in the proposed problem is a set of close to 165 images of the sugarcane in various forms. So we have, for instance, the plain sugarcane. We have sugarcane mixed with about 25% of leaves, and gradually progressing until the sugarcane is evenly mixed with leaves. So that we use as our input data. We also have a set of laboratory experimental values, including for particular interest, the percolation rate. So using those two, the percolation rate as the output and the images, the set of images as our input, we are trying to discern a nonlinear relationship between the images and the actual percolation rate.
And moving back to the conversation about neural networks, what is a neural network? This is a piece of computer software?
It's computational theory. So if you think about it, we try to emulate the way that a human brain thinks. So a human brain, in the same way, if I kick you in your foot, you don't feel the pain. I mean, the pain doesn't shoot right straight to your brain. It goes through several layers of interpretation before it is finally interpreted by the various sectors of your brain. In the same way, a neural network takes sets of inputs and then puts them through different activation layers and different other forms of layers until it gets to the actual output.
And given that we're talking about machine learning, I imagine that the computer is able to do that better and better over time. Is that correct?
That's correct. So tied in with that, the more input data that you have for a particular problem, generally the better your algorithm or neural network architecture will perform.
So to bring a third brain into this conversation, we want to welcome Reem Almadi. Reem is a master's candidate at Stellenbosch University with an interest in time series analysis and also in machine learning. And we wanted to ask Reem, how do we know if the computer is getting it right? How do we know if the machine is in fact learning appropriately in this context?
Thank you for having me. So as Tabang mentioned earlier, it's a process of simulating how humans think or how humans learn. And this is basically could be done by using different examples. Let's say that we have a child and we want to teach him how to differentiate between pens and anything else. So I will take a group of, let's say, red pens, and I will take the first one. I will show him the pen. I will tell him, okay, this is pen. I will take the second one. I will show him, and I will tell him that this is also a pen. And after that, I will take a cup. I will ask him to tell me what's that. So if he says that it's a pen, then in this case, he doesn't actually differentiate between pen and anything else. But if I take a pen and I ask him, what's this? And he was able, or he's able to tell me that it's a pen, then in this case, I will say, okay, fine. He's in a good level of understanding to differentiate between pens and anything else. So in the same way that machine could learn by having different examples, and in this context, we are talking about images for sugar canes. So we have these different images, and with every image, we have the adjacent laboratory measurement, which in this case, the percolation rate.
So this is to say that when those photographs that are being used for this exercise were brought by from the industry, there was already a relationship known between the photographs and the percolation rate, or the rate at which the water would move through the material. Is that correct?
Yes, but we had it in a numerical form where every image has a certain value represents the percolation rate. And what we've discussed among the group is how to convert this problem to suit the convolution neural networks, which is the algorithm that we're currently used to solve the problem. And we've done that by converting it to classification problem. So every image has to fall under one of 7 classes that range from 0.7 till 1.3.
And what are the visual characteristics in these images that you are using to decide which class is represented by which image?
Well, machine learning models or algorithms are built in a way that they will be able to differentiate between different images based on the colors, the features that could be extracted from the image. Let's say that we have an image of a face, then in that case the features will be the nose, the position of the nose with respect to the eyes, and how long is the distance between the eyes and the eyebrows, and all these types of features. So in the same way that it works for face, it will work for group of sugarcane, it will work for a photo for a garden, let's say.
And I suppose that's also part of some of the criticism for machine learning algorithms, because in addition to the features that Reem has already mentioned, the algorithm will also be able to learn features that are not hard-coded by the individual or the engineer. It will pick up features that we don't know beforehand and set them as relevant for the particular problem. So it learns to pick up other features which are important, which we might not know beforehand. Or so it's basically the algorithm is sort of termed black box in a way.
Okay, so the software that you're building or utilizing is looking at those images and trying to put them into certain categories. And you are telling it that it is getting it right or wrong at the initial stages?
Yes, so as I mentioned earlier, there is a stage where you need to teach the child how to learn, and this is by presenting different examples. In the same way, a machine can learn by presenting different examples, which what data scientists call it as a training phase, where you have different examples with their respective output. So you know the output for every image, and you feed it to convolution neural networks, and it train on these data. Later on, you have a set of data that is not presented to the, let's say it's a hidden data and it's never been presented to the model or this convolution neural network before. And in the testing phase, you feed the network with these new examples, and you ask the network to predict the output or to give you the class of those images. And after that, you should be able, as you know that for the testing examples, you already know what is the expected output, then the model will give you certain values as they predicted, and then you need to find the differences between the predicted and the actual values or the expected values. And the less difference between these two groups, the better your model is.
Fantastic. So you've got a situation where you can now, hopefully in due course, show the machine or the computer an image, and then it can tell you what you need to do, or what properties that sugarcane is likely to have, and therefore what amount of water is needed in order to optimally flush the sugar out of that sugarcane. So perhaps coming back to the proposer of the problem, what do you then do with this information?
We need data to control how the diffuser runs. So the output from this image analysis exercise will produce some of the data we need in order to make changes in the running of the diffuser so that we can minimize the amount of water we need to add in order to get the maximum sugar out of the machine.
And thereby improve the efficiency of the overall process and the profitability of the production.
Correct. Efficiency measured by the concentration of the juice we get out of the diffuser, yeah.
That's really powerful utilization of mathematics to improve a process. I'd like to move a little bit away from sugar and towards a conversation about how this experience has been. So, working with people from industry to solve a problem, how has that been for you?
Well, it's been quite beneficial because as researchers, we sometimes end up working in silos. You're a computer scientist, you're always in the computer science lab. But it's stepping outside of the classroom is actually beneficial because you can have all the theory textbooks in the world, but until you implement something, that really tests your understanding of what you have learned.
I would like also to add that since people are coming from different backgrounds and having different skills, this will help actually solving the problem in a shorter time. And that all goes to the fact that the flow of the information becomes so quick since we have a shorted or limited time to solve the problem, as well as the support from the academic representative as well as the industrial ones.
What have you found most useful out of this gathering of people together?
I think for me, it reinforces my belief in the principle of leapfrogging. So we find ourselves, especially in the African context, trying to catch up to the latest trends or the latest developments technologically from Europe and across the world. So in most instances, when presented with the problem, there is no time to study the theoretical underpinnings of whatever architecture you might employ. So you have to get your hands dirty. You have to learn by doing. Don't be afraid to break stuff in the process, and that's really powerful.
What was the most challenging part of this problem for you so far?
I think the first and the most significant challenge is the amount of data, because we do not have a lot of images and measurements that we can feed the network to guarantee having a good accuracy. And in this way, we have to find an algorithm or maybe a way to solve this problem by having more data. We're still thinking about a way where we can have more data, but that help our model to get better accuracy, but also without having too much information that could affect the result of the model.
Just to give the listener an idea of what DREAM means by the sparsity of our data set. So with some of these benchmark tests, Facebook released a data set. It contains 35 million images. Google has a data set that contains almost twice that. So with our data sets, we only have 165 images. So you can see the scale of the disparity that we're dealing with.
Absolutely. And how do you start to address that? Do you build that into the design of the process?
Yes, we've had to be very creative in our problem solving. Most of the techniques we're using are still cutting edge, still in developmental phases, still current research. But we're looking to get some very interesting results from the study.
Did you have any big aha moments during this exercise?
Well, something that jumps up is, as I mentioned earlier, it's important to step outside from the classroom. So most of the experiments that you'll do or whatever projects or assignments that you get, you will have sufficient data to deal with. You will have data that is not only sufficient but is optimal to the study that you're conducting. But once you step outside and actually take on a real world problem, the first thing you realize is that it just doesn't work like that. You will have to adapt and try and think creatively about how you will go about to solve the problem.
And I would like also to add having people from statistical background helps a lot in thinking about solving the problem because sometimes if you have less amount of data to feed to the model, you might be able to generate new variables, or let's say new factors that you could input to your model from the existing ones.
And perhaps the last question to Dr. Richard Loubser. Has this been a successful exercise? Have you gained what you hoped to by bringing this problem to the Maths and Industry Study Group?
Yes, I think so. The whole thing is that it costs money to generate data, particularly laboratory data. So at the beginning, we were asking the question, is it worthwhile going down this route? And I really think that the MSG workshop provides the opportunity to explore what routes are available, what routes will give us results, and then go back and actually develop those routes further. So I think it's a really valuable experience for us.
Fantastic. Well, it's been really exciting to hear a little bit more about this, about machine learning, about neural networks, and about sugar production. So something that affects all of our lives in this country and in the world, and we really look forward to hearing more about what your collaboration reveals. Thanks very much.
Thanks.
Thank you.
The South African Mathematics and Industry Study Group was founded by Professor David Mason in 2004 at Wits University and has created exciting opportunities for collaboration between mathematics researchers and industries facing complex problems. The 2020 event is hosted at the University of Zululand and is supported by the DSI NRF Center of Excellence in Mathematical and Statistical Sciences, the Herman Althover Trust, and the African Institute for Mathematical Sciences. This podcast was sponsored by the Center of Excellence in Mathematical and Statistical Sciences, an initiative of the Department of Science and Innovation and the National Research Foundation.